Today we're going to take a look at what happens when you have a couple of objects with different kinds of motion. In this situation, you have a person on an amusement park ride that's ascending at 1.00 meters per second, and then they drop their cell phone. It takes 1.85 seconds for it to hit the ground, and we'd like to know two things. Number one, we want to know how far up were they when they dropped the phone, and number two, how far apart are they when the phone finally strikes the ground. So in part A, we're going to take a look at what the cell phone is doing. I mean, it's part of the person. They're hanging on to it. So if the ride is ascending at a constant speed of 1.00 meters per second or a constant velocity of 1.00 meters per second up, then that's the initial velocity we can apply to that cell phone. So we'll place in here that VI is positive 1.00 meters per second. Now, since it is a dropped object and there's no other forces acting on it, we can assume that its acceleration it experiences is going to be 9.81 meters per second squared. So acceleration, I give 9.81 meters per second squared. It's very important that in this situation, since you have different kinds of motion in different directions, where they're ascending, they're going up, and the acceleration is down, that you acknowledge that the initial velocity has a positive value and the acceleration has a negative value. If you don't do that, you won't get the right answer. The time frame being scalar, no positive, no negative, just 1.85 seconds. And our distance, or in this case, really it's displacement, is an unknown in meters. So we take a look at the variables we have. VI, A, delta T, and delta D is one of those four acceleration equations we had derived before. We can use the one that involves delta D equaling VI delta T plus 1/2 A delta T squared. And we have seen a few examples in class where a dropped object would have an initial velocity of 0. This is not one of those situations, so we can't just cross off this term. We can't get rid of it. We have to incorporate it as part of the problem. But we can just plug it in, positive 1.00 meters per second, multiply the time, 1.5 seconds, plus 1/2 times acceleration, negative 9.81 meters per second squared, and time frame 1.85 seconds, and squaring it. That's going to give us a total value of negative 14.9 meters. So we're about 15 meters off the ground. So that's part A. Now in part B is asking how far apart they are, and we're really just asking, since the phone's on the ground, how far up is the person on the ride. So what you have to think of is what is happening in those 1.85 seconds while the phone is going up and then dropping finally back down to the ground. The person is ascending the entire time. It's a constant speed. There's no indication that the ride is accelerating. It's just a constant value. So for a part B, if we treat this as our part A and this is our part B, we could say that the person on the ride has a constant velocity of positive 1.00 meters per second. The time frame that they were ascending while the phone was dropping is 1.85 seconds, and our displacement is an unknown in meters. So there really is only one equation. It's the constant speed / constant velocity equation. So we can quickly arrange that in our heads. Just displacement is velocity times time. Velocity of positive 1.00 meters per second. Time frame 1.85 seconds. And that's just going to give us 1.85 meters. Positive 1.85 meters. Now, what it's asking for this question is a distance of separation. And what I've calculated in both part A and part B is displacement. And you think you'd want to add these things, but if we're looking for a distance, we don't want to use this negative and this positive. So as a final equation, I'm going to really state that the distance of separation is going to be the distance that the phone went up, or the phone dropped, sorry, plus the distance the person was going up. I'll just say student. So add those values up, and 14.9 meters plus 1.85 meters, and using our sig figs, 16.8 meters. And that's really just how far up the person actually is right now. So it's really important in this question, just acknowledging that there is a difference in sign for initial velocities and acceleration. As long as you apply those things, you'll be totally fine.